It's my pleasure now to introduce you to the Chair of the TERN Advisory Board, Professor Hugh Possingham, whose bio is so long that it will take the conference for me to tell you about it. So I'm just going to let you read it in the symposium book, and I now invite Hugh to the stage. Thank you.
Thanks a lot, Beryl. My name's Hugh Possingham. I chair the TERN Advisory Board. Beryl just reminded me that she has attended every board meeting since April 2010. And I thought, what sort of crime did you commit, Beryl, that you could attend what must be about 60 board meetings? My first task is to welcome you all, but also to acknowledge the traditional owners of where we are here, which is the Yagara and Turrbal people, and reflect on their environmental stewardship for tens of thousands of years of this place, and also reflect on the fact, of course, they are the first scientists, the first social scientists, the first historians, the first water scientists of this area, and the first economists. TERN is a very multidisciplinary thing, and we need to reflect not only on the science that they've done for tens of thousands of years, but also the stewardship of this land and the changes they made to this land. So we're not here observing some place that hasn't been altered by people. There's enormous changes that happened over those tens of thousands of years. But also I'd like you to reflect on the change to the people of this continent. As a young boy in an all-boys school in Adelaide, there was 1,000 boys. I was the only bird watcher. That did not make you the most popular person in the school, strangely enough. I don't know why. I would have thought it was. And people, even now, when I'm wandering around with my binoculars, which I do every weekend, say, "You're a bird watcher. That's a funny thing to do, isn't it?" And then you try and dig your way out of that corner and, you know, why am I watching birds and what's so interesting about it? And I sort of got sick of doing that. The last couple of years I sort of say, you're not a bird watcher? Because 500 years ago, everybody who lived here was a bird watcher. Every Indigenous person was observing nature. Actually, they named almost always the birds after, onomatopoeically. Tawong, what's Tawong named after? The Coel. Things like magpies, magpie larks, willy wagtails, common birds that they would have seen around their camps and areas and where they were foraged, those were named almost always onomatopoeically, which would stop us having language problems, surely, because the name is the call, so everybody knows it. So not only were they observing birds, one has to wonder what happened to society whereby we became so disconnected from nature in just 250 years, everybody noticing the environment around them, to now, well, it's not 1 in 1,000, thankfully. the number of people interested in natural history is booming. And to that point, you know, this is why it's such an exciting time to be part of TERN. Not only is the number of people who care about nature starting to return to those pre-European colonisation days, and we're starting to think more about nature, because I can tell you already the number of people who care about nature is booming, particularly since COVID. As Vice President of BirdLife Australia, our supporter base has gone heading towards 500,000 people. It should be 2 or 3 million people, but it's heading towards 500,000 people. But also the economists and the bankers starting to care about nature. We have a nature repair market bill. Whether you hate it or love it, a lot of what TERN does will underpin the workings of that bill that Tanya Plibersek is proposing. Treasury just released 50 wellbeing metrics for the nation, and there is a biodiversity metric, 1 out of 50, not that good. The British actually had 12 national metrics and 3 were about birds, so that's why the British are bird crazy. So we have 1, it's the Threatened Species Index. Jeff and Taylor are the stewards of that. It is a TERN product, and it is one of the 50 metrics that are now the wellbeing metrics of the nation. So TERN is delivering that, It's the first biodiversity metric. It created from the Threatened Species Hub, which was disbanded, and I can tell you 6 federal public servants tried to fight me to create that metric, oddly enough. Maybe not very oddly. And also another important outcome just from the last week is a whole series of TERN protocols about data collection are now being integrated into the way they run a whole heap of their stewardship programs. So it's not just TERNs collecting a whole heap of data that doesn't impact policy. This is now impacting the national agenda, the national conversation around the environment and what is well-being, but it's also affecting an enormous amount of data collection. So as Beryl just reminded me, it's like, how do we get Australia onto standard rail, not narrow gauge, not wide gauge, not everything else? How do we actually get everybody collecting more or less similar data in the same way? And they're not an easy task with ecologists, but we're actually making an enormous project. So I think it's an extremely exciting time that we are getting to this point where some of these things are agreed upon. And the only, I think, enormous challenge now is TERN has an enormous amount of national scale data, has an enormous amount of site scale data. I think this decade is going to be the push for regional scale data. So how do we actually amalgamate multiple sites over regions so we can produce regional environmental accounts? And I think that's something that TERN has worked on in the past, but it's something we all have to put a lot of effort into over the coming decade. So with that, I'd like to declare the symposium open. That's the words Beryl told me to say. I think it's going to be a very exciting couple of days. I really look forward to talking to you all and learning about the stuff you're doing. And I'd like to hand over to our newly minted patron. Well, he's not newly minted, he wasn't just born, Andrew Campbell, but apparently the inaugural TERN board chair and going to give us some words of patronising words. Thank you, Andrew.
Thanks very much, Hugh, and I'd also like to acknowledge the traditional owners of the lands we're on. It's great to reconnect with the TERN community. As Hugh mentioned, I was on the initial advisory board for, was it about 7 years, Beryl? But anyway, thanks for inviting me back. It's great to be here. And yes, I've no idea what a patron does other than be patronising, so I've got 10 minutes to do that. It's incredibly rewarding to see the continuity of effort that is represented in this room over the last decade or more, and given the funding landscape that's been applied, that we've lived in over the last decade or more, that's quite an achievement to keep ecological infrastructure running. So I can only imagine both there's been some people doing excellent work in Canberra to cobble funding together and to maintain continuity, but that's because of the work that they believe in the work that you guys are doing. So well done to everyone who's managed to keep things going to this point. In my day job, I'm the CEO until this Friday of ACR, the Australian Centre for International Agricultural Research. And we support science partnerships between Australia and neighbouring countries to help them improve their food security and so on. And just in the last week or so, the number of things that have sort of converged. The FAO has just put out its latest state of global nutrition and food security. And after several decades of the world managing actual agricultural science, keeping ahead of global population and the number of hungry and starving people going down, with COVID and the Ukraine, those trends have decidedly reversed. And so now we have very many people in acute starvation, but many, many others in severe food insecurity, and about a third of the world's population eating very poor diets. And particularly in our region, we've got neighbouring countries that have both stunting and obesity at significant levels in the same country. So the food system's out of whack. Those of you who have been tracking the startling graphs of what's happening at the poles right now, with sea ice and temperatures 4 and 5 standard deviations from the mean at unprecedented levels. So that the Arctic sea temperatures at the moment, the current record is further away from the previous record than the previous record was from the mean. And so it's absolutely startling. ICIMOD last week put out a new report on the Hindu Kush Himalaya, the third pole. And the glacial retreat is much faster than previously understood. Now, that's a watershed for 1/3 of the world's population. 2 billion people rely directly on the runoff from the water column of Asia. We've already seen in Pakistan what's happening with more volatile flows, but it's likely that by the middle of this century, overall, there'll be much less water, but what there is will be far more volatile, much worse floods, much more intense droughts. So, and my nephew works for Forest Fire Management Victoria. He's just got back from an incredibly demanding deployment to Alberta, trying to put out fires in boreal forests that have never burnt before, with 50 metres deep of organic material that you just can't put out, but you get bogged trying to get, you can't get a truck to it either. And so the challenges that we're grappling with and the evidence before us is absolutely startling. And I wouldn't blame ecologists for feeling despair at sort of documenting the destruction of nature with ever greater precision. So that dilemma between standing back and observing and while wanting to take to the barricades, I can fully understand that existential angst. But we do know that we need more and better science. And what does better science look like? It's collaborative, it's robust, it's transparent, it's accessible, all the things that you guys have been trying to achieve. And it's clear that we need it for top-down reasons, for the sorts of things Hugh was articulating, to make much better resource allocation decisions, and for society as a whole, and for governments to understand what's going on and where best to intervene. I'm encouraged to see reference in a number of the posters and other things too about this work being used for citizen science, and as Hugh mentioned, the 500,000 members of BirdLife Australia. We put out a little book recently on lessons from land care, where you know, we had the Australian experience, but land care has been implemented in about 20 countries around the world now, with no assistance from Australia or negligible assistance from Australia. From Aceh to conflict-ridden areas in the southern Philippines and so on. And the principle that weaves through that book is the principle of subsidiarity, the governance principle of trying to make the right decisions at the right levels, but in particular making sure that people at lower levels in the systems are empowered to make decisions that they need to make and informed to make decisions that they need to make. With the climates that we're already in, let alone the ones we're heading into, I think the subsidiarity principle is going to become ever more important. In Lismore, during the floods, when the SES was underwater, the tinny rescue flotilla was coordinated by local people on Facebook. Because when the SES is underwater, its comms aren't very effective. And the SES in Lismore, of all places, had 2 boats. So to say that we're unprepared for what we already know is happening is a gross understatement. So why didn't we have a system that's designed around locals on Facebook with tinnies? And that is the system. We need to empower people where they are and where they live to respond to the situation they're in with the data that they need to do so. And so I think it'd be great for you guys thinking about your ever more sophisticated infrastructure and your ever more sophisticated data handling and accessibility enablers to think about how does this get used by decision makers at a local community level, by volunteers with their Facebook equivalent of the old telephone tree, as well as how does it get used by a catchment management authority at a regional level, as Hugh was saying, or a state government or a regulator. In my view, we need to be rebuilding institutions. You guys are building some fabulous scientific infrastructure. In my career, and I'm in reflective mode because I'm giving a press club lunch tomorrow, and I figure they can't sack me on my second last day in the job. But just in my career, I've seen the abolition of the Energy R&D Corporation. Imagine if that hadn't been abolished in the 1990s. ARENA's doing a great job now, but we missed 20 years. Then the abolition of Land and Water Australia. So for the driest continent with the most variable climate to have its water research falling off a cliff. Then the abolition of the National Water Commission. The auditor, the independent scientifically informed voice for not just the Murray-Darling but the whole National Water Initiative. And the demise of other stuff which obviously wasn't statutory, but things like NCARF, the National Climate Change Adaptation Research Facility. I reviewed that in the early 2000s. It was doing fantastic work with local governments. And all of that work slipped away. So again, thinking about the fires and the floods and the fire ants and a whole bunch of other things, if we hadn't had such erosion of our institutional infrastructure, institutional amnesia and ad hocery and at times institutional vandalism, then I think we'd be far better placed today. So, as Hugh alluded, whether it's a carbon market, and in my view Australia absolutely needs a functioning land sector carbon market, but it has to be one that's genuinely delivering, or a water market, ditto, heaven forbid a biodiversity market, ditto. We're going to need really good information, and we're going to need institutions that can use that information, independent of government, robust, expert, using empirical data, that's transparent so that communities can see why decisions are being made and so on. We've lost our muscle memory for good regulation, as a number of scathing royal commissions, whether it's banking or aged care or robo-debt or whatever, have revealed. Australia has lost the muscle memory for how to do regulation well. Targeted, timely, effective. At the end of the day, environmental policy is really simple. We need to make behaviours that destroy nature less attractive, and behaviours that restore and protect and set us up for sustainability more attractive. Much juicier carrots, much smarter sticks, and sensible compliance and so on. Markets have a crucial role to play, but only if they are based on good information with guardrails and independent audit and other mechanisms to ensure that that information is translated into rewarding good behaviours and penalising bad ones. So whether it's mine site rehabilitation or fugitive emissions from fracking or whatever, we have not got that architecture right in Australia yet. The infrastructure that you guys are developing and the data protocols and everything that you're working on are incredibly important tools for society to be in a position to steward its natural resources far more sustainably and to bequeath a much more livable planet for our grandkids. The know-how to do that in Australia is extremely exportable. So right across our region now, we've got countries that are grappling with the fact that their monsoon is no longer reliable, that you can't set your clock by it, that you can't get that second or third rabi crop of rice in, that you need new options. We're quite accepting of the fact that the Darling River might be many kilometres wide, or it might have no water in it whatsoever. Other countries are now just starting to get serious variability in their stream flow, but their farming systems are not remotely set up for that. So the expertise that we have here in Australia, in my view, is a strategic national asset. Every bit as strategic as our military or anything else. And it's an asset that can be deployed for the good of our region and the good of the planet. And the expertise that you guys have developed is incredibly important for the country. I'm very sorry I can't stay for the whole symposium. I'd love to dive into it in much more detail, but I wish you well. So thank you very much. And remind me who I'm handing over to, Beryl. Ah, excellent, thank you.
Right. Thank you, Andrew, so much for setting the scene for us so brilliantly and laying out the challenge that's in front of us for the next 2 days so wonderfully. So I'm Belinda Medlyn from Western Sydney University. I'll be chairing this first session, which we're now very well set up for, thinking about the future, environmental scenarios, forecasts and predictions. So we have a very tight program, as you know, so the way that this is going to run, the speakers will just come up in turn, introduce themselves, they know how long they have to speak for, they're expected to get off at the end of that time. Can you put your questions into the app, please? We will have Q&A at the end. We will ask the speakers all to come out the front, and we've got 11 minutes at the end for questions and answers. So without further ado, our first speaker is David Hamilton from Griffith University.
Thank you, Belinda. Can I begin by also acknowledging the Jagera and Turrbal people who are the traditional custodians of the land on which we're meeting, and extend my respects to their elders past and present, and to any Indigenous people in the audience today. I'm going to begin actually by acknowledging someone who's sitting in the second tier of the audience, the second row, and that's Liz O'Brien. She had an awful lot to do with actually getting this project up and running. She lobbied very hard, and the result is that there's something like 12 years of work that's gone into this through various postdocs, through academics and through programmers. And it's a tool to build catchment resilience. Thank you. I thought I'd begin by telling you about water as the great connector. And it doesn't matter whether it's a tree on the landscape or a catchment that looks like a tree. Water is an incredible connector. It tells us about what we do on the land. And so when you think about a tree, for example, it takes groundwater and it puts it into the atmosphere. And our rivers and streams are basically networks. They're networks that connect the land, and they bring that water down into areas such as lakes and estuaries and the coastal ocean, which are essentially our sentinels of the way in which we've treated the landscape. And so really, this is just a little plug to say, let's connect the terrestrial and the aquatic. Let's connect our atmosphere as well, as closely as possible, because these are interconnected systems. Specifically, building catchment resilience, our program is about being able to attenuate some of the sediment and some of the nutrients that are lost from our landscape. And this is not something that I plucked off the web or taken from social media. This is my photo. We were caught out in floods, and I started to realise the impact of these floods is enormous. And the amount of sediment, the amount of nutrients that is being lost from our arable landscapes, we really have to be able to do something about it. The repercussions of that are that we're dredging ports, we're affecting stream health, our coastal oceans are also being affected, and loss of biodiversity as some of that sediment smothers our coastal ocean. If you go to the top of the headwaters of some of these catchments, some of them are in, shall we say, reasonable condition, but these are the sponges, these are the filters that essentially take out our sediment and our nutrients, that hold back some of the water right in the headwaters of the catchment. So these are very important, but when we go down into some of the other areas that have been impacted, you can see very clearly here how fences have been lost, infrastructure's being lost, our farms are losing some of their arable topsoil, and this particular area was really badly damaged, and it's in the Laidley catchment here in the west of Queensland, or in the west of Brisbane, sorry. So it really, defies comprehension in some ways to think of just each one of these floods, which are becoming more frequent, as we know, is really having quite a devastating impact in terms of the amount of sediment that's lost, the arable agriculture that's lost, the riparian vegetation also that's being impacted. So that led us to be able to look at what we're calling building catchment resilience, a tool that could be used to be able to evaluate the amount of sediment that's lost, the nitrogen that's lost, and also evaluate the costs simultaneously. It's aimed to slow what we're doing is we're aiming to slow the rate of flow, reduce erosion, and trap and transform nutrients and other pollutants to improve catchment resilience. So it's about being able to target different areas, and those are riparian and riverbank areas, hill slope revegetation, gully remediation, and wetlands, and using wetlands to be able to attenuate some of the sediment and nutrients. The tool that we developed is a modelling tool. It's designed to be applied at catchment scale, and what it does is it breaks up those catchments into planning units where we can, which are of a scale where we can target specific management actions. And so what we do is put in mostly georeferenced catchment data. We use essentially a modification of SedNet, and we use it in an optimization strategy to be able to look at what are the different options that we have to balance our cost with remediating the different areas that I've spoken about, which are hill slopes, the stream bank, and gullies. And ultimately, we can use a series of tools to be able to look at the back end of some of these scenarios. So there's some of the georeference data that we would put in, including the planning units, the hydrology, the ground cover, the hill slope, the rainfall, the soil erodibility. So standard GIS data that we can readily adapt to be able to put into the model. And the output that we get is essentially an optimization that offers different options for people, stakeholders, to be able to choose. So this is in a Pareto front, and some of this has been adapted actually from Hugh and Mark Zahn, which is a conservation planning tool, except it's being used in a hydrological sense as well. And so we start to look at different areas of the catchment and be able to say, well, let's choose some of these different options which have been optimised. So we're dealing with about 20,000 different scenarios, taking those down into about 5,000 or so different scenarios that stakeholders are then able to look at and say, well, what is possible? What might I choose? And then we look at the visualisation of those. And so this is just an example to look at some of the trade-offs which we look at in terms of informed decision making. And so we'll be looking at, for example, riverbank restoration, some of the planning units where we target that riverbank restoration, the hill slope restoration, in other words, planting trees in the upper catchments, and some of those combined actions. And that's essentially what we get. So here, for example, is around about 15,000 or so different runs. Some of the areas that need to be targeted pop up almost 100% of the time. So they're the no-brainers. We need to go into those areas and target some of our hill slope restoration. The areas that are darkened there also include gully restoration, and then we have areas that we might target for wetlands, potentially lower in the catchment. And ultimately, putting this all together, and we've been working with QUT, using some of their, essentially it originally came from their gaming software, to be able to put this into a visualization tool. So if the stakeholders have a particular run or scenario that they want to explore, then this is exactly what we're doing to be able to allow them to explore 1 or 2 or 3 different scenarios in more detail and visualize what would happen at a catchment scale. So the project is essentially largely complete now, and what we're doing is essentially looking for more opportunities. We think it's a very valuable tool to balance the costs, the nitrogen, the sediment, the flooding, all in one. And with that, I'll introduce Jurgen.
Thank you, and hello everyone. I'm Jurgen Knauer from Western Sydney University, and today I will present a project that's actually led by Belinda Medlyn. We called it the DAVE project, which aims to build a dynamic vegetation model for Australia and all the associated processes that are important for Australia, like fire, phosphorus cycling, and so on. And today, particularly, I'm going to present on a sub-project that focuses on grasses. And so when we think about grasses, we distinguish 2 main types that differ in their physiology. So we have C3 grasses and C4 grasses. They look very much alike, but they have a different anatomy, which leads to a different biochemical functioning as well. So in C3 plants, the CO2 concentration that's available for photosynthesis is tightly coupled to the one that's in the atmosphere. Whereas in C4 plants, we have a specialized anatomy that leads to an initial fixation of CO2 in the mesophyll cells, and then this is pumped into the bundle sheath cells where the actual photosynthesis takes place. So this leads to a concentration of CO2, which basically eliminates photorespiration, which gives the plant an advantage under high temperatures in particular. Why am I telling you this? This is really important in terms of how plants respond to the environment, because they're doing different things, or they're responding differently to global change drivers, actually. So we all know that C4 plants, they're doing pretty well under high temperatures. They're also more water use efficient, they're more nitrogen use efficient, especially under high temperatures, but they respond less to atmospheric CO2, so they have less of an advantage compared to C3 plants. So that's why it's really interesting to look at this question. But to start with, so we were taking the LPJ gas model as a baseline, which is a well-established global dynamic vegetation model, but it has a few limitations. In particular, it makes use of a concept called bioclimatic limits. So what the model does is it calculates a mean temperature of the coldest month. And if that is above a threshold, C4 grasses can grow. Otherwise, it's going to be C3 grasses. So that's very simple, and it also tells us, well, if we look into the future, under elevated temperature, we already basically know the answer, because that threshold is going to shift, and so will C4 grasses. So we weren't happy with this sort of simplification, and we are now currently working on a new model where these processes are represented more explicitly, right? So we have all sorts of processes in there. Some of them are sub-daily timescales, fast processes like photosynthesis, and others are in daily timescales like growth, storage, and that is in particular something that we consider important, is that the NPPs, or the carbon that you get, that can be used either for growth or it can be used to store it, right? We also have other processes in there. I mean, survival establishment is something that's important. And all of that is modulated by the availability of water. We have nitrogen in there, and plants do compete, right? So if C4 plants, for example, they grow better, then that might directly impact the C3 plants or any other vegetation types at that location. And really, what we want to do here is we want to get rid of these bioclimatic limits, and we want the vegetation distribution emerge from first order principles, so from the underlying mechanisms. That's the main goal. As I said, we're in the development phase right now, but we are looking at one site in particular, Sturt Plains, which is an ideal test bed. So it's an eddy covariant sites within the OSFlux network. And it's an ideal test bed because it covers all the extremes. So it has a growing period in the monsoon, and then it dries off completely in the dry period. And just to give you a bit of an impression of how we're doing at the moment, so we're pretty happy of how the model performs. There's a few things with the greening on and the browning off that can be improved, and the dormancy and so on. But I want to draw your attention to one time period in 2019, 2020 that is actually really interesting, because in 2019 the monsoon failed and the grasses didn't really grow. But also in 2020, the grasses did much worse compared to the other years, so they could only be half as productive compared to the other years. And despite the fact, I should say, that the blue line here is water availability, that you have plenty of water in 2020, still the grasses didn't grow very well. And we can sort of capture these legacy effects now because we simulate carbohydrate reserves in the plants. And what the model in particular did in this year, in 2019, after the first rain event, they started to grow, and they used about half of their reserves to grow in that year, which sort of weakened the plant, and that carried over to the next year where the grasses could grow less, right? So you see, we don't get the magnitude right at this point, but we have the mechanisms in there and the possibility to account for these effects. So as I said, this can be considered, these reserves can be considered as the memory of the grass, which is important for modeling grass persistence, but also things like competition or responses to grazing, right? So overgrazing, for example, is also a problem that is related to carbon storage in plants. And what we also can do is, very quickly, we can look at elevated CO2 and elevated temperature, and how different grass types respond to it. Though this is just a very preliminary result, so I don't want to go into much detail. What I want to mention is that we have now really good data sets at the continental scale that allows us to evaluate and validate the model at the larger scale, and that's where we want to get to, really to apply this model for the whole of Australia and to look at the shifts continentally. And last slide, that's the team I'm working with, and yeah, happy to answer questions later. Thanks.
Good morning, my name is Lucia Morales. I'm going to be presenting about the Queensland Special Biocondition Framework. This is a joint project between the Queensland Herbarium, the Remote Sensing Center, and the Joint Remote Sensing Program from Queensland University. But first, I would like to acknowledge the Turrbal and Yagara people in which land most of this research has been carried out. I'm going to talk briefly about a background of what is biocondition, and how it relates to the Special Biocondition Framework. Then I'll provide a brief overview of the modeling approach and the data that went inside that. Present you the product that we will be releasing, give you a bit of outlook, and most important, where to get the data. So the Queensland Herbarium has been working for quite a while on developing a framework to assess vegetation condition in the field. and this is known as biocondition. And basically, biocondition is a measure of the relative capacity of an ecosystem to support a suite of species that are expected to occur in its reference state. A reference state is basically an area that is largely undisturbed and has mature vegetation, so that we can use as a sort of benchmark to compare other areas to. So basically, to get a biocondition score, people go to the field and assess a series of structural attributes and biodiversity measures, and compare that to the reference states, and is able to assign a biocondition score. As you can see here, like the ones on the top, the ones on the top were the ones with good condition, and the ones on the bottom with bad condition. So basically, we have already a good framework to assess biocondition on site, but what was really needed was a tool to be able to assess biocondition in any point of the state. And this was mainly needed because we wanted to have a more holistic reporting on vegetation, not only like on extent of clearing, but also on the quality of the vegetation that was being cleared, for example. And this was like, to respond to this need was why the spatial biocondition approach framework was developed. It works basically under the same premise as the biocondition on the field by comparing two reference areas, but instead of comparing the structural attributes of vegetation, we are actually comparing remote sensing characteristics within the same regional ecosystem. And now a brief, I'll oversimplify overview of how the modeling approach actually works. So we start with the regional ecosystem pre-clearing mapping, which provide us with information about homogeneous areas in terms of environment and vegetation. And from this, we have a bunch of training data that because of each regional ecosystem have a set of defined benchmarks, we can score all of our training data against that. So from all that training data, we're able to extract a series of remote sensing predictor variables, and the ones that are in good condition, the sites that are in good condition will come to be like the expected values in terms of remote sensing. So they will be the ones that will tell us how good looks like in remote sensing terms. And the other sites here are the ones that we're gonna compare that to. And this difference between the expected values and the on-site values is the information that will be used as an input to train a gradient machine regression, a gradient boost regression tree model that will actually provide us with a set of rules that we will use to actually predict the value of biocondition in any point of the state and produce our map. So I have been talking about the modeling, but what data went into that? So most of our training data came from the QBIS database that is publicly available in TERN. So we actually assessed this data for quality and came out with a database of about 17,000 points after dropping more or less 60% of the data. We spent quite a lot of time on the curating process. So 17,000 points for Queensland. And as predictor variables, as remote sensing predictor variables, this data came mostly from 4 main data sets. The final model have 9 predictor variables. The one in bold are the ones that actually made up the final model. But 2 of these data sets were a 3-year time series of fractional cover of temporal statistics based on Landsat of the green and dry fraction. And actually the green fraction, the variability on the green fraction and the minimum value of the green fraction were like one of the main important feature values for the model. The other 2 data sets that we used were the dry seasonal fractional cover based on Landsat for 2019. And also we use as input the growing season metrics for 2019. And this is the product that we're going to be releasing now. So I have been talking about like that we did the modeling over the whole state, but we are actually now only releasing 2 data sets for 2 bioregions. That it would be the Brigalow Belt and Southeast Queensland. These data sets have a temporal, temporal dimension of, so they will show the condition on 2019, that's why, and it has a resolution of 30 meters. And basically, well, that they are composed of the prediction of biocondition and the upper and lower boundary of the prediction interval. So we actually did a field validation assessment of this data using 231 points selected through a stratified random sample in these 2 bioregions. We actually obtained encouraging results, a good agreement between the predicted and the observed of 0.7 and a mean error of 15. And just to, so part of this data doesn't cover all land covers. These the ones that are here and at the top are not included. Plus, it doesn't include areas where there were not enough sufficient reference data for specific REs. And just a bit of an outlook. So modeling biodiversity modeling condition for biodiversity is quite complex, particularly because you cannot really directly observe biodiversity with remote sensing. So given these limitations and given the sort of training data that we are having, we actually are happy with the result of the model. And well, as next steps, we're gonna be updating this product for 2021. And we're gonna include other bioregions, plus the publishing and of the methods and results, and also getting more training data and more validation data and getting more benchmarks for the regional ecosystems that are missing benchmarks. And well, the most important part is where to get the data. The data will be available in TERN and in QSpatial as well. All the code will be publicly available in GitLab, and all the predictor remote sensing variables are also available. So please get in contact if you are interested in any of that. And finally, this project is really a work of a lot of people. And yeah, and particularly of Chris Penny, Teresa Ere, and Leonardo Harkey. And well, it's also the result of really an effective interdisciplinary collaboration between institutions. And well, thank you for listening. I will go back.
I just wanted to start by saying thank you very much to Beryl, Mark, and all the TERN team for putting this symposium to bring us all together. It's so lovely to see so many familiar faces in Brisbane here today. And thank you also for the opportunity to present our work on Queensland's newest and TERN's newest SuperSite called Fletcherview. And I'm presenting this work on behalf of the team at Fletcherview, as well as our massive army of collaborators. So my background has been in modelling. So I worked in big modelling projects, mostly for the Queensland government, things like the Paddock to Reef for the Great Barrier Reef modelling, and then the GRASP and Aussie GRASP modelling, which is an operational modelling framework for Queensland. And so today I'm going to share with you today our journey and some stories of how a bunch of modelers went back to the drawing board and out into the field to measure data, and this was to fill some fundamental gaps that we had in our work. And I did not know as a modeler what I was getting myself into when I started this work. And so the biggest thing that the biggest challenge that I faced was the cattle, because one of the things we did want to quantify was the effect of grazing on carbon and water fluxes. And so we wanted the experiment to run as a cattle station, and so everything that we installed needed to be fenced off from cattle, and I didn't even know how to build fences. And if I reflect back on my time in this project, from all the planning and the installation and all the field work that we've done, I spent most of my time thinking about and talking about fences. And the way I learned that was how any teenager would learn things, and that was by watching YouTube videos, until I learned so much about fences I could talk about it at the pubs in Charters Towers all night. And so every bit of equipment had these fences. So the things I'll talk about today is data and the power of data, especially for modelling. How we used modelling to firstly inform the measurements that we took, but also to help with our understanding and bring it all together. And then lastly, the massive strength of all the collaborators, and there's a lot of collaborators in the room today here through TERN and through the Queensland Government and CSIRO that really helped move this project forward. So this is why I initially started this work, the map of Queensland, when I was working on modelling pastures with the grass and Aussie grass models for the whole of Queensland. And we had a massive gap in wooded grazing land. So 80% of Queensland is under grazing, and half of that is under wooded grazing. So that's 40% of Queensland where we didn't really have any good data to evaluate our models. And that's the gap that I went to fill. And when I started this work, Lindsay Hutley, who runs all the flux sites in the Northern Territory, he joined in as a mentor to help me with this work, and he pointed out that work in savanna ecosystems for carbon and water fluxes was a gap in Australia, but also globally. There's not enough data sets, and savannas are very important ecosystems. It's about 25% of Australia, 20% globally, and it contributes to about 25% of the gross primary production globally, which makes it our planet's very important ecosystem carbon sink. And so the map on the right is all the TERN supersites. So there's 16 TERN supersites, and Fletcherview is the one with a big dot because it's the new one at the moment. And Jamie Cleverly and I are very excited that it's still the biggest dot on the map at the moment. So that's the one I'll be talking about. So it's in far north Queensland, west of Townsville, 2 hours west of Townsville in the Burdekin River catchment. So it's quite a big project. The parts of the project that I'm most interested about and that my project is funded to do is evapotranspiration, and in particular characterizing and understanding evapotranspiration, and specifically how the different vegetation components that make up a savanna ecosystem, so the trees, the shrubs, and the grasses, how they affect evapotranspiration. That's my main goal, and that's also a gap that we have in savanna modelling, is the partitioning of evapotranspiration. And in the sort of work that I do with pasture modelling, that's quite important because we need to be able to specifically know how much water is available for the grasses and how much water is available for grazing. But there's a lot of other groups interested in that as well for the partitioning of ET, and there's very few data sets where people measure all components of the water balance. And that's one of the things we're trying to do at Fletcherview. So this is a conceptual model of grass, but it could just as easily be any vegetation or any water balance model where the components that we model are runoff, soil evaporation, deep drainage, tree transpiration, evaporation from the tree canopy, and then from the grass transpiration, it goes on to biomass, and then from the grass biomass, animal production as well for our model in particular. And in terms of the monitoring we do at Fletcherview, these are the sorts of things we've been monitoring. So the main focus is the evapotranspiration from the flux towers, subflow sensors to measure tree water use. Soil moisture is huge. We do a lot of soil moisture monitoring here. Deep drainage calculations, vegetation biomass, vegetation cover, and heaps more measurements. This is a video of the Fletcherview, just to give you an idea of how open the savanna systems are in North Queensland. So the average annual rainfall here is about 650 millimetres, so it's quite open. So Eucalyptus brownea is the main species here, and for people who know about land types, this is the box land type. There's a lot of shrubs here. The Carissa bush covers about 30% of the landscape here, which is here because of the combination of multi-year droughts and overgrazing, and it's a big problem that DEF is trying to address at the moment. And for any soils people, this is a melon hole, so the Gilgai sort of landscape with soda soils and vertisols. So it's quite a complex landscape in terms of soils as well. Oh, I forgot to mention the flux tower is 25 metres high, so it's twice as high as the tree canopy, and the predominant wind direction is easterly, and so the flux tower faces in an easterly direction. This is the very first cut of the modelling that I did with GRASP. So this is taking the best parameters, for this particular land type and modelling it. So the the blue line is the measured data. And as you can see, we're not doing a very good job with the GRASP model at the moment, and that's specifically why we're, doing these sorts of measurements to help us improving the models. Like, it might be just a parameterization job where we can parameterize these land types so that, a large chunk of Queensland in areas with trees. But, so we'll be, using this to help us with parameterizing, but also improving the model. And you'll notice there's a lot of gaps in the data as well, and that's, been one of the challenges in doing the field work. Very quickly, just with the AURA model. So this is the Australian water balance model that was developed by CSIRO and the Bureau, and it does a much better job. I won't go through all the other modelling for the other, but just present the data we collect. Soil moisture is quite important, so we do that using 4 different methods. So continuous soil moistures, 1 metre soil probes, the Cosmos sensors, which Matt Stenson will be talking about straight after me. That's just been installed in April this year, but we also do a lot of gravimetric soil moisture. So every time I go there, I try to get a 1 metre core of soil moisture, and that's what I use to calibrate all the soil moisture. We did a very comprehensive soil characterisation at this study with the help of soil scientists from the Queensland government, because soils underpins all the modelling that we do, and we wanted to get a really good handle on the soils. And I also use the soil data to estimate the recharge rates. And some of the legends in this space in Queensland are Mark Silburn and Andrew Biggs, and Andrew actually helped me to do the characterisation at this site. And one of the main things I learned from doing this work with them, everything from planning and doing the work with them, all the way to the lab analysis and looking at the results, it made me realise just how much work goes into people that collect the data. It was so easy for me to get some soil parameters of Big Z and never realising just how much work goes into, some numbers that we plug into our model. Pasture biomass is huge. I've got a 25 by 25 metre pasture exclosure where we do very extensive measurements to get pasture growth parameters. So I've got 2 seasons, so 2 growing seasons of data now, and that's what we use to parameterize the pasture model. But also to extend the work out to the grazing industry, we've done pasture biomass transects over the whole paddock, just so that we can take our research and the work we're doing and extending it out to the whole grazing property. So at any given time, we know how many animals are on there. I won't talk about this. Hopefully Will talk about this in his talk about all the flash work with the LiDAR and the terrestrial laser scanning. Tree transpiration is the latest thing we've been working on, getting measurements of tree water use for the stand. That gives us, I'm going to have to skip through all these slides now, to give us a really good measurement of tree water use to tie in with the ecosystem ET that we measure with the fluxes, and that's been the most exciting part of this project. And the key strengths of this project has been the range of data that we measured and the incredible value of all the collaborators that joined to help us get all the data. So these are, I wasn't able to talk about the SEP flow by ICT, but Ben will be doing a talk about that later in the session, so you'll get to hear about that sort of work that's been happening at Fletcherview. But thanks very much, everyone. And then I'd like to introduce Matt Stenson from CSIRO for the next presentation.
Good morning, and thank you all for coming. Oh, I'm going to get near the microphones, aren't I? So I'm a bit of a ring into this. This is not so much a modelling presentation, but a presentation around some work that I've been coordinating. So I coordinate one of the platforms, the sensing platforms in TERN. So there's 4 platforms within TERN, and they all are sort of work at different scales, both temporally and spatially, and the processes they sort of look after. So I'll be talking today about the landscapes platform. So we are the continental view of TERN. So that's the Australia-wide, high temporal, high frequency, long-term sensing of Australia. So you can see the sort of different scales up there across where TERN works. So we have landscapes up the top, and then we have the ecosystem sort of surveillance, doing the national scale, but more plot-based sort of on-the-ground surveys, and then we have the processes, the SuperSites, the flux towers, and the long-term monitoring of those sort of processes. So TERN Landscapes has been, I guess, when TERN was restructured in 2018, 2019, Landscapes came about mainly from the old remote sensing OSCover platform and the soils platform, which had previously done some work for TERN. And it's included multiple partners over the last 5 to 6 years. You can see all the different institutions and universities there. Too many people to name, but there's been a lot. The project's had 4 project leads. Initially it was Mike Grundy and the soil space, and Alex Held in the EO remote sensing space. And nowadays it's Ben McDonald in the soil space and Glenn Newman in the EO space. And we have some science leads as well, who you might know their names from sort of different work and calibration over the years. So I've picked out a couple of the keystone products, as we like to call them. So these are products that we've published through the Landscapes platform on behalf of TERN. And the first one I picked out is the Soil and Landscape Grid of Australia. So this was initially developed prior to the current iteration of TERN, but it's been continuously improved. So it's a national scale modelling of different soil properties, and underpinning all those soil properties are a whole range of what they call covariates. So essentially they are modelled or observed physical properties that are then used in a machine learning type approach to develop these, in effect to interpolate the measured data or to infill it to come up with these national scale grids. So the grids are available depending on which one. Some are at 90 metres, some are down to 30 metres now, especially in the covariate space. So you can see that they cover a whole range of different soil physical properties. And like I said, the covariates that sit under them also have a whole range of different properties that are all essentially useful. To give you some idea of the impact that this has had, prior to this coming back sort of more directly into TERN space, it was the second highest by volume downloaded data set from CSIRO's DAP, and the highest was the astronomy data, and that's just purely because it's massive, so that's why it probably had the highest. Another one we've been working on is continental scale soil moisture. So there are a few soil moisture products available. The Aura model has soil moisture, AWAP, there's been a few others done over the years. So what we tried to do was come up with something that we could use what's called a data model fusion approach, where we could take real observed data in a model, but also then force the internal model using remote sensing so that we could actually keep the model on track using sort of different styles of data together. So it's a continental scale model, runs on a daily time step at about a kilometre grid, has 2 different buckets. But one of the great things we did with this that hasn't been done with the other models is we actually integrated the soil physical properties from the Soil and Landscape Grid of Australia and came up with volumetric estimates over time. So it has about almost 20 years of model data now that's available on soil moisture across the continent. As Joe mentioned, we run the Cosmic Ray Soil Moisture probe network across Australia. So the Cosmos probes are a little bit different to most of the other soil moisture probes you see. What they actually do is they measure cosmic rays and then what's absorbed in the water and what's not, etc., and work out sort of in a broad area of about 30 hectares of the average soil moisture for that area down to a reasonable depth. So they give you a different view on soil moisture, and we found them very useful, especially for the remote sensing products, to use them for validation because of the larger footprint they have. So depending on which probe, some of them have been running for sort of about 2012. Some of them are much newer. Fletcherview is one of the newer ones we've just put in. And they're available hourly time step and all the data, including the other sensors, the rainfall, temperature and humidity for the sites you see on the right. Some have been retired, the red ones you can see. I don't know what's going on with the slide, but we've also developed a product, national scale evapotranspiration. So this is also a gridded product. It's a blended product, monthly, 30 millimetre resolution, looking at the AET for the continent, and that gets updated seasonally and is available as well. Another interesting thing we did, and this is something we would like to do more of in other areas, is the federation of data. So soils information was available in a whole range of different disparate databases. You know, there'd be state government, private companies, federal agencies, etc. Universities had soil data. You know, slightly different descriptions, different formats, different databases, etc. And this federator actually just doesn't download the data and warehouse it. It actually just brings them together on the fly, so you can query across all the different soils databases around the country and extract data that's in a consistent format. So you can see there it's got a web API for anyone who's into that sort of stuff, and then you can send it queries through either through the web or through programming languages and bring back data in a consistent way. Doing something like this would be very useful in a whole range of different data that are available through Australia but not federated like this. Some of the other work that was done for us, mainly by our partners at UTAS and University of Adelaide, is around developing protocols. So a lot of drone data is becoming very important, especially for us in validation of remote sensing products. But when it's captured, it's hard to get it in a consistent, you don't know what they've used when they capture it and how they've captured it and processed it. So they developed these protocols and tested them around being able to have a consistent way, so that when we get the data together, we can actually use it together and it's useful. So they're being rolled out at the moment through the TERN field teams and TERN surveillance. So just some of the other stuff that we've had put out. We did a whole range of infrared spectral analysis on all the soil samples that were in TERN surveillance Owens, and that's available. Sean Levick and others have been doing some work around, and Will Woodgate, around terrestrial LiDAR at different sites, and Fletcherview was one of them Joe mentioned. That data should be available soon. Looking around the national sort of modelling approaches for fire, and so we've had a representative that's been, Stefan Meyer's been representing TERN on the national sort of committees and looking at a consistent modelling approach across the country, which has been really helpful. We also helped in the land chapter of the State of the Environment report, led by Kristen Williams, and some other stuff coming out there as a covariates I mentioned, and just some other stuff that's coming out very soon, including some high temporal resolution Himawari products from the stationary satellite, and some very long-term optical data from the AVHRR data archive we brought back online. And thank you very much.
would like to begin by acknowledging the Ngunnawal and the Ngambri people, who are the traditional owners of the lands where I live. In this presentation, I'll be talking about how we applied community-level modelling to identify the fingerprint of recent climate-driven ecological change in Australia. As we are all well aware, since 1910, land surface temperatures across Australia have warmed by nearly 1.5 degrees Celsius on average. Changes to rainfall patterns have also been experienced variously across the continent. For example, notable seasonal rainfall declines in the southwest of Australia since the 1970s have occurred, and more recent declines in the southeast. Extreme fire weather has increased, the extent of snowfields has decreased, and sea levels are rising. This climate change has ecological consequences, and a burgeoning literature has explored the implications for biodiversity and options for management. Change can be sudden due to extremes of weather, or more gradual due to population decline, as individual species' varying capacities to adapt locally are exceeded. While considerable investment has been directed toward forecasting how climate change influences species and ecosystem redistributions, fewer studies backcast how much ecological change has already occurred. This example from Adapt NRM for vascular plants shows species compositional change projected using generalised dissimilarity modelling. 3 of our outputs that depict different types of change, locally similar, becoming novel, and disappearing, are combined to derive this composite index. But given that land surface temperatures have already increased by about 1.5 degrees Celsius on average, we should also be looking backward at how much pressure to change is driven by climate change using the same species compositional dissimilarity modelling approach, which takes into account the local influences, soils and landforms, as well as the interacting effects of climatic averages and seasonality. This would enable several outcomes, including an understanding of where and how much ecological change is now committed in the system, even if not yet physically evident, provide real-world examples of compositional change linked to model predictions to inform interpretation of future ecological change projections, and provide for better informed design of future management actions to help biodiversity adapt to change. This project, undertaken between 2015 and 2019, aimed to use GDM-based measures to predict areas of the Australian landscape where natural ecosystems appear under different levels of pressure to change, and test and strengthen the GDM-based modelling of biodiversity for forecasting ecological change by relating actual observations of change with modelled predictions of change. In designing our analytical strategy, we considered the traditional use of GDM in projections, which applies a space for time substitution, and a new approach which we developed through this project that applies spatial temporal model fitting using GDM-based methods. Among the types of observations we considered available for use or testing the effectiveness of hindcast GDMs, we could include anecdotes from a national survey led by Suzanne Prober, species occurrence records aggregated by the Atlas of Living Australia, and fixed site repeat visit monitoring. We ruled out the fixed site repeat visit monitoring due to limited data and that data is rarely harmonised into central repositories. So the next couple of slides I will provide results from 2 examples using aggregated species occurrence records. We first checked which biological groups had sufficient records for a time series analysis. There are millions of time-stamped species observations in the ALA. Here's an example for plants. And there are also millions of observations of birds from Birds Australia and other observers. From the graph here, you can see that it might be feasible to evaluate patterns since around the 1960s. From the traditional approach to GDM, we just used spatial presence information and projected by substituting with climate from a different time period. we fitted models using 1990 centred 30-year climatic averages and backcast to 1960 centred climatic averages. Of course, these models included soil and landform variables too. The difference between the two time series is summarised for 3 types of change: locally similar, becoming novel, and disappearing, as used in Adapt NRM work. The results show extensive areas of compositional stability, which are green, widespread and variable areas of compositional change pressure, as reds, blues, and pinks. However, the results are confounded by a signature of climate observation stations. These analyses could now be repeated using the new Bureau of Meteorology's Barra climate reanalysis data, which wasn't available to us at the time we undertook this work. The new spatial temporal model fitting approach was developed by Andrew Hoskins using pairs of species observations across time windows. In this way, a pattern of species matches and mismatches is used to predict ecological distance in space and time. Each observation is related to its antecedent climatic averages in the model. Initially, we varied the length of antecedent climatic windows to decide the window to use in the model. For birds, we selected 51 years based on peak model performance. For vascular plants, we needed to extend the climate window beyond 60 years to confirm the maximum model performance had been reached. Applying the 51 years of antecedent climatic conditions, we modelled compositional change in bird communities between 1965 to 2016. The solid blue line represents average change in continental dissimilarity, compositional dissimilarity, and the shaded blue areas show the 95% distribution of estimates around this mean. Continent-wide, a trend of change in bird community structure is emerging, and from this result, the average change since 1965 appears to be around 15%. We hope this presentation inspires the need for further investigations into backcast models to evaluate evidence of ecological change already committed under current levels of climate change. Thank you for listening.
Good morning, everyone, and thanks very much for having me. My name is Will Woodgate, and I'm a research fellow at the University of Queensland. And today's presentation, I'd like to talk about the Tumbarumba long-term research site, which is a TERN site. I'd also like to thank the various collaborators that make this possible, including CSIRO, University of Melbourne, ANU, University of Queensland. And in today's presentation, I'd like to focus on some of the research undertaken at the site in the context of bushfire recovery, and also highlight some of the international and domestic collaborations that make this possible. I'd just also like to acknowledge the Yagara and Turrbal people on the land on which I am speaking today, and pay my respects to their elders past, present and emerging. So the Tumbarumba research site is one of the longest running sites, flux house sites in the Southern Hemisphere. Now it's currently its 23rd year of operation. It's a tall, productive native eucalypt forest site located in southern New South Wales, also in a state forest that's been used for over 100 years for timber production. It survived major disturbances such as insect attacks, fires, droughts, heat waves, and also lightning strikes. So as part of the Black Summer fires of 2019-20, our site was impacted, along with around 90% of the state forests, which was 50,000 hectares of native eucalypt forest. So here are some photos of the impact of the fire at the site. It was a very hot, fast-moving fire, so it incinerated all of the understory at the site, but left the canopy intact. So here we've got some images of all of the ground-based infrastructure that was completely wiped out, but thankfully the tower was still intact. And the equipment at the top of the tower was largely intact as well. Here's a photo from 2 months post-fire where we start to see some epicormic regrowth of the gum species, but the ash species, which is the other main species, was completely wiped out as it's a fire-sensitive species. Moving on a bit further, so 5 months post-fire, we see some grasses starting to emerge that are quite short, and also the epicormic regrowth starting to take off a lot more. We were lucky enough to get 5 days of data capture to test the functionality of the flux tower equipment 5 months post-fire. And also this was in the middle of COVID, so it was very challenging to operate in this environment. But what we see here is a graph of net carbon flux on the y-axis and incoming solar radiation on the x-axis. And we've got the observations 5 months post-fire in red, so we can start to see that the site actually turned into a minor carbon sink after these 5 months, and the background signal is the blue dots and the blue line, which is quite a productive forest globally, typically pre-fire. Fast forward over a year since the fire, we had a visit from the AusPlots TERN surveillance team to collect some very detailed inventory data at the site. We start to see here that there's a lot more grasses. Interestingly, after the fire, so the canopy was not consumed during the fire, but the radiant heat damage meant that all the leaves were damaged and disappeared after a number of months throughout the fire afterwards. So the AusPlots team, we got very busy with measuring detailed inventory metrics. It was pleasing to see that the ash species were really recovering quite well after the fire. So with the regrowth and sprouting, over 100 seedlings per square metre were recorded. And also we recorded over 60 species after the fire, which was kind of matched the pre-fire levels. So the system was rebounding really nicely after the fire. So over a year after the fire, we can see that the carbon sink is increasing, but it was only about 50% of pre-fire levels. So this is the same plot as before, but 1 year afterwards. So this is a flux tower site that's part of a global network of flux tower sites called FluxNet. And FluxNet do a lot of work with harmonising data sets to make it fairly available for modelers, remote sensors, and everyone else who's interested in the data. This site has been downloaded, the data from this site has been downloaded over 5,000 times from this one synthesis exercise from 2016. If the site was a researcher, it's got its own scholar profile. There's been 130 plus peer-reviewed publications that have used data from this site since its inception in 2001, and it's been cited over 18,000 times. So some of the canopy structure information we can collect from LiDAR sensors. So we have a collaboration with a NASA science team called JEDI, which is a spaceborne LiDAR mission. And so on the right-hand side, we've got a plot of the vertical vegetation structure profile from the JEDI sensor pre and post-fire, and contrast that with a more high-fidelity terrestrial laser scanner profile on the left-hand side. So we can see they match up quite nicely, and we can see the big impact of the canopy structure change pre and post-fire from these two LiDAR techniques. Although one of the limitations of the spaceborne LiDAR mission is it's not a wall-to-wall mapper. It's very sparse in space and time. So for example, straight after the fire, it took us a year to have an observation from the JEDI mission within a couple kilometres of the site. So one of the ways of filling those gaps is with what we see here, which is a leaf in situ LiDAR sensor, which is a specially designed sensor that sits embedded in the site and monitors through time autonomously. And that gives us really high fidelity canopy structure information at a daily time step, which is really unprecedented for a data collection approach. And so we see here a brand new network of in situ canopy structure measuring devices called StructNet. And so it's good to see that Australia is quite well represented in this new network. Also on the canopy structure side, we typically were collecting hemispherical photography, pointing up at the canopy to see differences in the density of the canopy. So you see here plant area index that decreased around 75% pre and post fire. And this was part of a collaboration we have with our European colleagues as part of the European Space Agency and this GBOV project, which I'll talk about now. So GBOV stands for Ground-Based Observations for Validation of the Copernicus Land Surface Products. So Copernicus is the fleet of satellites that the European Space Agency operate. that are fantastic for providing space-based products for land surface processes. So they are very interested in getting in situ validation data to test the accuracy of these products, and so they reached out to us because we collect such a broad suite of measurements to help them. So at this site we collect over 70 continuous data streams. Here, this land surface validation exercise, we're interested in 7 core land surface products, and we collect them all at this site, including land surface albedo, the fraction of photosynthetically absorbed radiation in the canopy, the fraction of vegetation cover, land surface temperature, soil moisture, and also top of canopy surface reflectance. So on the spectral side of things, we have a custom-built hyperspectral and thermal sensor, which gives us a satellite capability at the site to fill spectral and temporal gaps that we don't have available to us from the satellite at present. So this is a system here that collected sub-daily data collection located at the top of the tower. It would point down the canopy and build up a nice hemispheric or panoramic field of view. And this is an example of the imagery that was collected from the hyperspectral sensor as a true colour image, and also the thermal sensor, the thermal imager below as well. So this enabled us to develop retrieval methods that are fit for purpose at Australian sites. And also a key point here is all the data that we do contribute to our international colleagues is really important to have Australian data that's unique in its structure in terms of its really vertically inclined leaves and clumpy canopies, to make sure that this data goes into verifying and developing satellite products that are fit for purpose and work over Australian conditions. Another spectral capability that we have at the site is a hyperspectral sensor that measures solar-induced chlorophyll fluorescence, which is a really faint signal or energy emission of vegetation when it conducts photosynthesis, which gives us a direct window of insight into photosynthetic activity at that point in time. And so here we collaborate with our European colleagues again, who have what's called the FLEX science mission, which is a fluorescence explorer mission run by the European Space Agency. And we also contribute to a global network of spectral flux tower sites called SpecNet at the same time. And also lastly, I'd like to acknowledge that we also have an aerosol monitoring station, which is really important to be able to link what we measure spectrally at the top of the canopy with what satellites measure at the top of the atmosphere, so it characterises the atmospheric composition, which is really close by to our site as well. And with that, I'd like to thank you for your attention.
So if I could ask the speakers from this session to pop up on stage. Yeah, okay. And we've got Kristen online as well somewhere. Okie doke. Is that everybody? That's everybody. Fabulous. So we are not taking questions from the audience. The idea is that you write your questions into the Q&A in the app. And if you're like me, you haven't discovered that yet. So I would encourage you to, I think Mark will explain after, yeah, okay. So I have a generic question that I want to ask everybody. But after I do that, we might get Mark to explain how to ask questions in the Q&A. So my generic question for all of you, in the absence of questions on the Q&A, so this session is forecasting and prediction, and this isn't the first symposium that I've been to where we had a session about forecasting and prediction where very few people actually talked about what's coming. Because I think in Australia we have a bit of a reluctance or a lack of capability to really think about what's next. And it does worry me a lot that we're not factoring that into our planning. But perhaps that's just me. I wonder if I could get each of you in turn to reflect on what do you think is coming next, and how do you think that your work could be applied to questions about, you know, what do we expect, how do we adapt to what's coming, and, you know, what are the issues that stop you doing so, if there are issues indeed. So David, I'm sorry, you're first on the list. Your presentation was super interesting and it's a really nice tool, but I wonder, you know, how do we use it to address what's coming in the future?
Hope you can hear me.
Yep, that's on.
One of the things about building catchment resilience is it's a little bit different to the way that we normally look at floods, which is often very short term and often designing grey infrastructure to be able to cope with what's about to come. The idea behind building catchment resilience is it's about green infrastructure, and that is that infrastructure that's there that builds through time and that is able to actually mitigate what we know is about to come, which is obviously more flooding and greater propensity for drought at the same time.
Yeah, sorry, we're having some issues with people not being able to hear online. Have we been able to turn the microphone on the live stream? Not that I can see anything.
Is the microphone working now? Is that better? Or?
It's working in the room.
It's
okay. Should we come up to the stage?
Maybe. Yeah. Why don't you do that? David, pop up here because they couldn't hear you. Just recap briefly.
I was going to say that many of the tools that we use are often quite short-term predictions, and some of those relate to hydraulic models and look at the impacts on, particularly on grey infrastructure and the consequences from storms. What we're talking about is much longer-term investment in green infrastructure, which is around being able to go into the headwaters of catchments and be able to essentially mitigate the extremes that are going to occur through a long-term investment in that green infrastructure. If the grey infrastructure fails, it's often catastrophic. If the green infrastructure fails, in other words, if it's investment that's obviously been knocked out because of storms, then that is also a consideration, and it does have potentially a higher risk, but it's got a much greater and longer term impact than what we might be doing at the bottom of the catchments.
Jurgen?
Yeah, good question. So in the context of process-based models, what I presented, I think the strength of these models is looking into the future and looking into conditions that are unprecedented right now. That could be elevated CO2 and temperature or other aspects of climate change. So that goes in decades into the future, but I think these models are also useful in terms of forecasts, in like speaking of the next days and months. That is really much more relevant for land planners and managers such as pastoralists. That could give them much more of a management decision tool. I think that's something that's also underused in that sense right now.
I'll let Lucia come next.
I guess, well, the model I presented was more based on not necessarily in the future, but also on actual data. And well, we hope that these sort of models for vegetation condition will really help the uptake more into other parts of the system, like be inputs for informing natural capital accounting, or be inputs to informing how are we doing in terms of protecting biodiversity. Yeah, and mainly that, yeah.
Joe, are you up next? So someone's figured out how to work the live Q&A. So you also have an extra question, Joe, which is, do we
Can I-
need more Savanna sites?
Yes. Yep. The short answer to that is yes, we definitely need some, and hopefully in Queensland. But there's a massive gap in WA as well, so it'd be nice to have one up there. So we've got the whole of Northern Australia. But in terms of the prediction question, that's definitely the motivation for some of the work that we do with the Aussie grass model. So that's already used operationally to do predictions, although my role in the work is mostly model development, evaluation, but everything that I do does get rolled out through the grass platform. But some of the challenges that are coming that we're very conscious about is the change of how trees are going to change in the landscape, you know, with things like carbon credits, reef credits, biodiversity credits, you know, what the impacts of having more trees in the landscape, you know, will mean for things like overgrazing. But the other things that we're really conscious of at the moment is, you know, the effects of the multi-year drought, the multi-year droughts that we've had, which has caused overgrazing and which has really shifted the pasture species composition and, you know, the composition of shrubs in the landscape. But also with climate change, we're already seeing the growing seasons shift, you know, the start of the growing season change, and then just seeing what happens when we run out of water before the season ends. So that very much drives the work that we do.
Yeah, prediction, it's a bit of a hairy one, isn't it? I think that prediction around isn't as useful unless we know where we've come from. So the ability to have long-term monitoring and be able to actually put it in context is really important. That's something TERN does, which is really good. I think also the interrelationship between the different things that TERN monitors and how they affect one another, you need to understand that to be able to properly develop and parameterise models. So, you know, that long-term prediction gives you that sort of view as well. The real danger is the fact that, I mean, the past doesn't necessarily predict how the future is going to unfold. It may give us some broad indicators and they're useful in their own right, but it's sort of those step changes in behaviour of natural systems that I think that we're really going to struggle with. And yeah, in retrospect, we might be able to figure out what happened, but yeah, it's a challenge.
Exactly. That's what us modelers are up against. Kristen? Kristen, you're up.
Sure, can you hear me okay?
Yep.
So just in terms of what is coming, climate change and more pressure on the land use change as people are adapting to that change. But we've known that for decades, and climate change is now our lived experience. And what it's inspired the work that I presented was the fact that most of our biodiversity modelling has been focused on projecting ecological changes into the future. This is the generalised dissimilarity type compositional modelling, but it's hard to imagine what that actually means in reality. So the work I presented today aimed to backcast those models as a basis for understanding what the change means in a real world sense. And if we have that understanding of being able to visualise what that change is from existing lived experience, then that will enable us to better interpret what our projections will mean on the ground into the future. And this information can then help identify where we need to prepare to intervene in some landscape. And so I'm hoping that the work that I presented today in terms of demonstrating what is possible inspires more backcasting models as well as forecasting to support adaptation planning to help biodiversity adapt.
Yeah, great. Thanks, Kristen. Lucky last, Will.
Thanks, Belinda. So what I know about modelers is they're a little bit greedy and they love lots of observations. The more the better to test and develop the models further. So from a remote sensing perspective, it's very exciting because there's an explosion of new data sets that are available, especially hyperspectral from space, which gives us species abundance, potentially diversity. especially drone platforms now as well, and high quality LiDAR acquisition. We're getting beyond visual line of sight capability, so we can go further, really high density. So we're getting better spectral resolution, better spatial resolution, better temporal resolution in all aspects at different platforms. So especially with LiDAR, I think having the ability to get structural metrics, which can supplement or replace our inventory approaches to get tree structure down to centimetre level of branch detail will be a game changer into the future. So, thanks.
Right, so thank you all for your last minute answers to my question about the future. I think we all know that we've got great challenges ahead of us, but please join me in thanking everybody for a great session.
Thank you, everyone. I actually worked out how to, if the people would like to leave now, thank you, that way, exit. I worked out how to do the Q&A. My question didn't get asked, but if you have a look at, on your emails, you would have got an email this morning from the symposium organisers, and they did put a URL in there to get to the app, and then you have to log in using the password, etc. And then I discovered that you have to, once you're logged in, you find the program, there's a little arrow on the side, and it takes you to the thing that lets you list your Q&A. But if that's all too much, come and scan the QR code, because we're going to morning tea now, and that would probably be your quickest way in there. So thank you. We'll see you after morning tea, which we start at 10:45. Thanks.